So good morning, welcome everyone to today's class, which is 20010 CIP4, and that's implementing mixed analog and digital circuits using core independent peripherals, or what we abbreviate as CIPs. So my name is Priyabrata Sinha. I am in the MCU 16 or 16-bit microcontroller applications group, and with me is Sean Chin, who is in the 8-bit microcontrollers application group, and today we will be talking about core independent peripherals together. So in your embedded application, are you finding that you need to use a lot of external analog or digital circuitry, which you would obviously want to eliminate or reduce as far as possible? Or maybe a lot of your CPU bandwidth is getting consumed by handling or managing all these analog and digital signals, your ADCs, DACs and so on. So if either of these questions the answer is yes, then hopefully this class would be very helpful for you in pointing you to some good core independent peripherals that would be applicable for your mixed signal application needs. So obviously we'll here's the agenda for today, and we'll first look at the various core independent peripheral modules that are available on our devices, both 8-bit ones and 16-bit ones, and then hopefully you would be able to choose the right subset of these peripherals for to meet your applications requirements. And then we'll learn the features and benefits of each individual module, and basically get a brief idea about how to use and configure these in your application. And finally, and perhaps most importantly, is that we should not look at each core independent peripheral in isolation, but think of combining them in various creative ways. So we'll look at some various application examples where we are using multiple peripherals in conjunction with each other to implement a slightly more complex system and offloading a lot of peripheral management tasks from the CPU. So broadly, here is the agenda for today's class. First we'll look at the basic philosophy of what core independent peripherals are and why you would want to use them in your application. And then we would look at various modules that are useful for implementing some mixed analog and digital circuits, or even managing analog and digital signals in your application. So one of these is the configurable logic cell, which is present on both 8-bit and 16-bit microcontrollers from Microchip. Then we'll look at some modules that are present only on the 8-bit devices, like the signal measurement timer and temperature indicator. And then we'll move on to modules that are present mainly on the 16-bit devices so far, like the peripheral trigger generator. That's a very powerful module that we'll look at in a little more detail. And some of this may be familiar to you if you have sat for the CIP2 class, so I would say there is a little bit of overlap because we have kind of segmented it by application areas or example applications. Then we'll look at programmable gain amplifier, or PGA, and finally comparators and opamps. So first let us see what CIPs, or core independent peripherals, are. So these are basically various peripheral modules in our chip which are designed to be somewhat self-sustaining or autonomous. So once the CPU the software has configured these modules, they should go off and do their various assigned tasks somewhat independently of the CPU. So it should not need CPU intervention to repeatedly feed it data, or to change various modes, or to wait for certain peripheral events and so on. So ideally these peripherals should work independently and not require much CPU horsepower. And most importantly, these should really be thought of as a collection of peripherals. So by each each individual module may have its capabilities, but when you combine multiple such modules together, you can really implement a nice, efficient, and even a complex system in many cases. So why would you want to use CIPs in your application? First and foremost is obviously you would want to reduce your CPU overhead, because normally we see that in embedded applications a lot of the CPU's bandwidth is consumed by managing peripherals, enabling, disabling, triggering various events in multiple peripherals. So a lot of these routine and mundane tasks can be offloaded from the CPU, and so the CPU can really focus more on the innovative part of your application. So maybe some algorithmic computations, some special computations that you would need to perform in your application, and leave the mundane peripheral management tasks to these core independent peripherals. And one Side effect of reduced CPU overhead is obviously you can run the CPU at slower speeds now. So, you can reduce your clock speed, and so the CPU can run at lower MIPS, which means its power consumption is reduced obviously, and CPU is one of the major contributors towards power consumption of any microcontroller. So, if that is reduced, it is really beneficial for your system. In fact, in many cases the CPU can go into sleep and stay in sleep for most of the time and periodically wake up based on some peripheral events and perform some computations as needed. And one thing that is very useful in the context of today's class is that the system hardware complexity is also reduced, because a lot of external circuitry or logic can be eliminated, and that would reduce your system cost and space requirements as well. So, in the specific context of mixed signal circuits or signals, why would you want to use CIPs? Because they really help in generating complex waveforms that you may not necessarily, ordinarily get from regular peripherals like output compare and so on. Complex waveforms, complex protocol signals and so on. And in many cases you might want to control some delays in your application. So, for example, you might have some peripheral event, and a certain time period from that you would want to, let us say, sample the ADC or convert some analog signals, and many applications are very timing sensitive. So, these kind of precise delays can be controlled using some of these core independent peripherals, and also signal limits. So, we are dealing with various analog signals. So, in many cases they could go off limit and exceed its upper threshold or fall too low below its lower threshold, and we have to be able to detect such conditions or scenarios very quickly and respond to them without having the CPU get interrupted and perform some corrective action. So, this peripheral module should be able to work in conjunction with each other to detect such abnormalities and take corrective action, maybe shut down some machinery and so on. And in many applications we required temperature measurement, both as a safety mechanism as well as maybe for the actual computations that are part of that application. So, these one of these modules allows you to measure the ambient temperature directly. And of course, in your application, especially more complex applications, you might have multiple states. So, your entire algorithm may be implemented as some kind of a state machine. So, some of these core independent peripheral modules can be used to implement this state machine, or make peripheral events jump from one state to another, reconfigure peripherals in some cases. So, these state machine transitions become very easy and efficient when you are using multiple such peripherals. And of course, externally you might require some circuits to perform signal conditioning. You might be dealing with very small valued signals and need to amplify them, or you might do some level shifting or even some signal filtering. For example, if you have an audio input, you would need to band limit it to based on the sampling rate that you are using in your application. So, you would need what is called an anti-aliasing filter. So, that is just one example of an external signal conditioning circuitry that you might need in your application. But using some of these core independent peripherals, you can eliminate those kind of external circuits, and we will look at those as we look at the individual modules. And finally, and this is especially true for 8-bit microcontrollers, is that some of these modules, in fact one of these modules allows you to compute PID loops outside the purview of the CPU. So, independent of the CPU, you can compute a PID loop or perform some multiplications and feed the result back. So, it enables more complex computations even on very low cost on small memory devices. So, which are the various core independent peripheral modules we will look at today? The first one is of course configurable logic cells, or CLC. Some of you may have attended the CIP1 class, which was entirely focused on CLC. So, here we will be touching upon this peripheral very briefly and more in the context of combining it with the other peripherals that we will see. Then signal measurement timer, which is present on PIC 16 devices, and temperature indicator as well. So, both of those are 8-bit specific core independent peripherals. Then there are some 16-bit core independent peripherals, and the primary one is peripheral trigger generator, or PTG. And this is mainly present in most of the dsPIC 33 family devices. Then some devices, but so far it is mostly the SMPS family devices or digital power devices from the dsPIC 33E family, They have on-chip programmable gain amplifier or PTG module. And of course, most of our, in fact, all of our 16-bit devices have an analog comparator, multiple analog comparator modules in different flavors, so different range of capabilities, but they all have an analog comparator. And some also have integrated op-amp modules, which is very versatile and can be connected to each other. So for example, some PIC24FKM family devices have it, and most of the dsPIC33 devices. So before we move on to specific peripheral modules, here is a pop quiz. Which of the following is not a possible benefit of using a CIP? You can run the CPU at a lower speed, or CPU bandwidth can be freed up to run more innovative algorithms, or you can use a microcontroller which does not have a CPU. Yep. Or implement complex state machines. The answer is number 3, use a microcontroller which does not have a CPU. I mean, to really drive innovation, your CPU might still need to perform some computations or execute some very innovative algorithms. So having a CPU is beneficial anyway, and anyway all microcontrollers have CPUs.
That was my question, is there any microcontroller without a CPU?
That would be really core independent. But then there would be nothing for you to do. So. Yeah. If the peripherals are doing everything, then it's hard to differentiate between one application and another, or provide some real innovation. So now I'll hand it over to my colleague Sean, who will go over some of these the 8-bit specific core independent peripherals.
All right. Morning, everyone. So right now I'm going to cover some of the 8-bit specific peripherals that we have. The first one is called configurable logic cells. I say some familiar faces, so you guys might know what's going to come up in the following. So CLC is a peripheral that we put in the die with configurable basic logic components. So when we see basic logic components, we have gates, flip-flops, and latches that you can use. And those are built in the die. So you don't have to buy discrete components to finish your job in terms of coming up some logic combination and do signal conditioning, maybe negate a signal or doing AND gate. Right? So it is very flexible in terms of interconnectivity. It can literally map every available signals internally from every other peripherals, and you can steer your output to all of the internal peripherals you have. So what we can do with CLC? Well, it can connect peripherals with each other in a unique configuration. As I mentioned before, you have a wide variety of selections in terms of input signals. It can generate complex signals very easy because you can fit it into those signals and come up with your logic on your own. Or it reduces components count and PCB area. In that case, you don't have to buy like discrete components like 7/4, and then you have those logic components in the die that you can use directly. You got faster event response. Everything is routed internally. Operation, it can be operational while the CPU is in sleep or idle. Well, save power, of course. So what do we have exactly? For the CLC, we have a 4-input, 1-output logic block. And when we say logic block, we specifically means one of those 8. You have AND OR gate, XOR, AND gate. You have SR latches and D latches. You have JK flip-flop, and D flip-flop. All the inputs and outputs assignment on the CLC can be assigned to many of the peripherals internally, and of course, externally on the pin. So in a nutshell, what we have a combined logic components that you can choose, as we can see in the previous slide. You can choose one of the 8. And you have a bunch of input that you can choose from. Right now we have available in total 38 different input selections you can select. And inside of the CLC, what we have actually, well, if you ignore this output part, which is just signal conditioning and event generation interrupts, then what we do really have is a 2 major pieces in the CLC. The first one is the input data selection stage. Here is where you select, okay, which input I'm going to use for my CLC. Either it's from other peripherals or from the external pin. The second stage is your logic function. This is where you configure your CLC as one of the 8 basic logic components. So in the input selection, what we really have is we have in total available 38 inputs, which again, you can choose from various sources. The signal itself and its negation got fed into an array of AND gates, and by writing those bits, which is mapped to a register, you can choose either the signal itself or the negation of itself. And then all those signals get ORed in the final stage and get output. Of course, you can choose the polarity, so you can flip it around. So this basically is your input selection stage. Choose your signal, write the bits in the register, and figure out, okay, which signal am I using, which signals are all together. And this is going to generate something called G1. We call it as the input candidate signal for the second stage. And for each CLC, we have 4 blocks of this output for the next stage. So we have G1 through G4. And this is, again, just a reference. If you really want to figure out which bits or what value you should write to those registers to decide which signal you're going to choose, by writing those, you are actually making your selection gate as one of those. But you don't necessarily have to figure out on yourself, and by looking into the datasheet and write the registers, you can choose it. You can choose to use the MCC, the Microchip Code Configurable tool, which is a GUI-based interface where you can just click on different components, click on different input selections, and the tool is going to generate the code for you. So you don't have to write the code. All right, so those are the first stage, right? Remember that we say we have 4 of those, generating G1 to G4. And then in the second stage, you take those input and you configure your CLC as one of the 8 different logic components. And you fit those candidate input into the second stage to finish your job. And they're going to form one of the 8 different logic components that you have. Any questions? Awesome. Now, the second one we're going to introduce is Signal Measurement Timer, SMT. Well, SMT is nothing but an enhanced version of timer 1. So this timer running can run at FOSC, which is 32 megahertz at the maximum for 8-bit. And it has a 24-bit timer, or let's say counter. So this timer is running, and what it can do pulse width acquisition. So think about it as an enhanced version of input capture module. What you do with input capture is you are waiting for some event to happen on the pin, either falling edge or rising edge, and then when it happens, it will capture the timer register and put it in the register that you can use, right? So SMT somehow is working as the same token, but is a little bit enhanced in terms of clock frequency and its bit resolution. And also it can capture falling edge and rising edge without any configuration change. So it can capture both of the edges at the same time. In that case, well, naturally, you will think about it as using it for period acquisition and duty cycle acquisition, right? So you have a PWM wave coming in, you can use SMT, and it will capture those events and give you the value or the number of counts between those events will naturally give you the duty cycle and your period. Well, also, it has a gated timer window modes. So internally, it actually has 2 independent counters with individual captures. So those are used individually for each of the events, rising edge and falling edge, right? It will generate interrupts on any event, of course. And we do have a counter overflow detection. So whenever it overflows, it will generate an interrupt and set up a flag, and an overflow happens. So what we can choose as the clock source for the SMT and its input? Well, it can come from, again, like other CIPs, a various selection of inputs internally or externally. You can choose it from PWMs, other timer overflows, like your timer 1, timer 2. Can come from CCPs, capture, compare PWMs, CLC output, zero cross detection module, ZCD, and it can come from comparators and, of course, external I/O pins. So inside this SMT, actually, what we do have is, first one is your control logic. This determines, OK, what mode am I working with? Do I working in a synced window mode, or do I just like doing simple period and duty cycle capture? And another major piece, of course, is just your timer, which is a 24-bit. And you can see we have two individual 24-bit buffer here. It's keep counting individually. So a quick timing diagram that we can see as an example for this SMT, how does it work? What we have is we have a clock signal coming in. This serves as your counting clock. And whenever you want to use this one, you set this SMT go sync to high. So this tells the SMT clock, OK, now waiting for events. And then when the event happens, start counting. So the first event we see on the signal input is the rising edge. So the note here you have to pay attention is whenever this happens, it takes one cycle for my timer really to sync up. So that's why you see a little bit delay here. So that's a one cycle delay here. So when the rising edge happens, it takes one cycle for this guy to catch up and start counting. So it will start counting until it says the following edge, which is another event, right? Then the value of your counter will be captured on the following edge of your clock. And this will be latched into your pulse width register, which gives you the duty cycle. Then when the other rising edge happens again, it will be captured on the following edge of your clock. And this will be captured in your period register. And when those two events happens, you can optionally generate a flag and interrupt. So this is a basic example how your pulse width and duty cycle capture can be working. And you can set a register to make it working repeatedly, so you don't have to like do it over and over again. Whenever there's a new value coming in, the two registers going to be refreshed on the new values. And I think I just talked through those. All right, so what we can do is it? Well, the first naturally inspiration of using the SMT is, of course, I can measure my PWM signals. So I fit my PWM signal in to my SMT, and then I can read out the counters for my duty cycle and my period, which is trivial. Another possible usage is we can use it to tune your internal oscillator. So what we can do here is if I have a stable external reference clock, I can always fit this clock to my SMT because I know this is a very stable clock. So depending on the value I'm reading from SMT, I know if my internal oscillator is running too fast or too slow because this SMT is clocked by my internal oscillator. So if I know, OK, my expected value of my duty cycle or period of my internal clock is such and such, but it's a little bit off, then what I can do is writing the OsTune register to tune my internal clock. So this is like internal clock calibration process. Any questions on SMT? Awesome. All right, so the next peripheral that we're going to be looking at is temperature indicator. So this is like specific for some of the 8-bit devices. What we have with temperature indicator? Well, it's an internal temperature indicator. And what it uses transistor junction threshold voltage to produce variable output. So it's depending on the junction threshold voltage, right? So you might guess it might not be very accurate, but it's a very inexpensive way of doing basic temperature indication. We have two working modes, high range and low range. Well, the high range mode allows for a wider temperature range, dynamic range, so you can sense a little bit wider in terms of temperature. However, because you are trying to sense wider, you have to apply a higher voltage on that because we are using the junction voltage threshold, which means we have more junctions. More junctions, you need more voltage to drive them. The low range mode allows for a wider power supply voltage range. So you don't have to apply that much voltage to drive them because we have less junctions. So you just need 2 or 3 volts to push them through, but you don't have the wide range of dynamic range of the temperature sensing. One important note for you guys if you want to really use this temperature indicator is it should be calibrated by users during application production because, again, it is using the junction voltage threshold, right? So it can be different. There's a little bit variance between each batch of productions because the junction can be distorted. Well, the voltage internally is available as an ADC input source. So when you do this temperature indicator, you can just hook it up to your ADC and read a ref value from that. Basically, what you have in terms of determining your temperature is you can follow this equation here. Again, those two constants, the offset and the slope, should be calibrated when you're doing your production. We've been talking about the high mode and the low mode, so how they really work. Well, again, as we mentioned before, the high mode has a wider dynamic range, which means we are using more junctions, and the low mode has less dynamic range, but wider power supply range. We are using lesser junctions. So actually, with high mode, we are using 4 junctions, and with low mode, we're using 2 junctions. So your equation is going to be modified slightly based on which mode you are. There's a little multiplier there, well, indicating how many actually junctions you have. So if you have 4 junctions, that thing is going to become 4, and if you have 2 junctions in the low mode, it will multiply by 2. Because we have more junctions here, so you need to provide at least 3.6 volts to drive it through. And if you only have 2 junctions, you can go below 3.6 volts. So this is the temperature indicator. So what we can do with it? Well, we usually use it to measure the operating temperature of the silicon. So it's in die. It does not measure the ambient temperature. It can go from -40 to +85 Celsius. Because again, it is using the junction voltage threshold, so it is not that accurate, but it can be used as a temperature threshold for a more accurate temperature indicator if you want. But this is in the silicon, and you can use it as an inexpensive solution if you don't really need that accurate temperature sensing. All right, any questions on temperature indicator? Pop quiz. Okay, which of the following module is not presented on the 8-bit? SMT.
Space module.
Space module, yeah. Awesome. So those are basically the 8-bit portion of the CIPs that we want to cover today. And now I'm going to hand the ball back to Priyo, and he's going to continue with some awesome 16-bit CIPs.
Okay, so now that Sean has gone over some of the 8-bit core-independent peripherals, I'll now move track a little bit and talk about some of the peripheral modules that are present only on the 16-bit devices, mainly the dsPICs, but also the PIC24Fs. And the first module we'll look at is the Peripheral Trigger Generator, or PTG. So this is a very versatile and powerful module that, those who have attended the CIP2 class would have seen some of its capabilities, but we'll go over that in this class as well. So, what is a PTG? PTG is nothing but a programmable sequencer, or basically it's basically a set of step commands that you can set up in advance, and then it will go off and execute those steps autonomously independent of the CPU. So, the CPU is going on executing its instructions, and the PTG module is also executing its assigned steps, and it does not require any CPU intervention at all in most cases. So, what kind of steps can it execute? It can perform things like waiting for certain peripheral events, looping. So, you can execute a block of steps repeatedly. So, it supports loops, it supports delays. So, you can use the PTG module to insert some delays between different peripheral events. So, it is basically intended to synchronize or harmonize the operation of multiple peripherals and signals, or even event states in your application. It has an internal watchdog timer that we will look at in a little more detail. But as you can see from this diagram, the PTG module can talk to pretty much the entire set of peripherals that are present on a 16-bit device, which means it can enable a lot of complex interactions between all these modules. So, what are some features and benefits of the PTG? Of course, the obvious one is that it saves CPU execution time, right, because it is going off and doing actions in parallel to the CPU. So, it is almost like a little a logic block, or kind of a micro CPU that cannot perform computations, but can perform simple peripheral management type things like sending triggers, waiting for peripheral events, inserting delays, looping between different steps, and so on. So, the first question that might come to your mind is these step sequences, how do you repeat them? You can repeat them either using conditional or unconditional loops, and we will look at those commands in a little more detail. But what you need to know at this point is that the PTG module has its inbuilt loop counters. So, it has a couple of loop counters named C0 and C1. Which are independent of any W registers or any CPU registers. These are all registers that are internal to the PTG, and it also supports unconditional looping. So, you can go off and execute this same set of step commands repeatedly as long as you want, until the CPU decides to disable the PTG module. So, these step commands are basically a set of control registers which you set up in advance, and then those get executed by the PTG module. In most of our devices that have PTG, there are up to 32 step commands. Some smaller memory devices might have up to 16 or 24. So, the next thing you might wonder is whether the execution time is programmable. And here, by execution time, I do not mean the execution time of the CPU, which is obviously determined by the clock speed of the device, but here it is how frequently the steps get executed. So, once step 0 has executed, when will the next step be executed, and so on, and then step 2 and so on. So, that is configurable, and you can change it on the fly as well, because there is something called a step delay timer. So, by configuring and enabling the step delay timer, you can insert a delay between successive PTG steps. So, you can exactly control how frequently these PTG step commands get executed. And it can also add some delay between specific events, because it has its own 2 inbuilt timers. So, these are again not consuming any general purpose timers. These are timers T0 and T1 that are internal to the PTG module itself. So, it can simply initiate a delay wait state as a step command, and then in the next step command it will perform further actions. Now, one of the main functions of the PTG is to wait for certain peripheral events or synchronize different peripheral events, but the first thing that comes to mind from a safety or robustness perspective is what happens if the peripheral event that it is waiting for never happens. And the PTG does have a safeguard against that kind of scenario, which is basically a deadlock scenario, because it has an inbuilt watchdog timer. So, whenever it executes a step command that is waiting for a certain peripheral event or trigger to occur, and if that event does not occur within a certain specified time delay, the watchdog timer times out, and what will happen is it will disable the PTG module. It will not reset the device, it will just disable the PTG module, and I think it generates an interrupt also to the CPU. So then the CPU can later on take corrective action or re-enable the PTG again. And the other thing is whether the timers and counters are dynamically configurable. So why is this important? Why do you think this is important? Any ideas? These are the PTG timers and loop counters, because in different parts of your application or different stages you might need different delays, obviously, or you might need to implement the same loop at different times with different loop counts, because note that there are only 2 loop counters and your application might well end up requiring more loops than that. So that is possible because you can through a PTG step command itself you can update some of these timer and counter values or counter timer limits. So there are some commands that does that. This is the PTG add and copy. So we will look at each of these step commands in more detail, but this is just to give you a broad overview of what benefits it provides. And finally, it can generate interrupts to the CPU, because in some cases the CPU does need to perform some computations and update some maybe peripheral parameters, right. For example, if you are executing a control loop, you might be sampling some analog signals from an ADC, let us say in an SMPS application, and then you would use those conversion results in your PID control loop or whatever. So that PID control loop does need to be executed by the CPU, right, and it needs to be executed by the CPU at the right time. And how would it know it needs to execute that? The PTG would tell it to execute it by generating an interrupt request. So as soon as it receives as soon as the ADC conversion results are ready, it can send a interrupt request to the CPU, and then the CPU can execute its control loop. So broadly, these step commands can be categorized into 4 types. There are input event control step commands, which are basically commands that wait for certain peripheral events or input triggers. And it could wait for a trigger signal to go high, or it could wait for a trigger signal to go low. So both variants are provided, PTG WHI or PTG WLO. So wait for high or wait for low. Then on conversely, it can also generate triggers, which are basically output triggers to various peripherals, and there is a command that does that, PTG trig. And of course, it can generate a trigger to the CPU as well through PTG IRQ. So all these are specific values. These step commands are basically nothing but values that are listed in the data sheet that you need to write to the step registers, step 0 through 31. So these are not registers as such, these are just values that you write to those step registers. Then there are then there is a PTG strobe command, and that's a very important one, especially in the context of analog digital signals, because that allows you, for example, to change some module registers or different module registers on the fly just using the PTG step commands. For example, you might need to change the ADC channel selections. In different parts of your application you would need to sample different signals, but you are using the same ADC, right, or you may be using a device with only one ADC, and that you can do using this PTG strobe commands. It will basically transfer a certain value to that ADC channel select register. So here it is updating a register that is not internal to the PTG, whereas this PTG add or PTG copy commands update registers that are internal to the PTG, like the PTG timer values, the PTG counter values, and so on. So there are various control functions, like some of those include enabling the PTG watchdog timer and so on, or enabling software input trigger. Then there is finally there are flow control commands, which is conditional or unconditional branches. So there is a PTG jump command that is basically an unconditional branch which you can use to execute a block of step commands repeatedly infinitely until the CPU disables the module. And then there are conditional jumps, PTG jump C0 or C1, where the certain loop count is maintained in counter 0 or counter 1, and then as soon as that count decrements to 0, it comes out of that loop. So in each of these flow control commands you specify which step you will be jumping to, so you can very easily implement a loop. We had talked about input triggers or waiting for various hardware or peripheral events, and there are up to 16 hardware input triggers that are supported on the PTG module, and these could be either edge triggered or level triggered. So, a peripheral signal or event, as long as it stays high, it will keep triggering the input trigger if it is level triggered, whereas edge triggered would only trigger it once when it goes high. And then which are these modules that can generate triggers to the PTG? There could be PTG, the PWM special event trigger, which happens when the PWM time base rolls over, or the master time base rollover in the case of the high speed PWM. Input capture events, output compare events, comparators could also generate a trigger. So, if some signal goes beyond its limits, it can immediately trigger the PTG, and the PTG can send a trigger immediately to some other peripheral or maybe shut down some module. Then ADC conversion, and this is a very important one, because in many cases the PTG would be used to wait for an ADC conversion result to be complete. So, that the ADC, the CPU is not held up in polling for that ADC conversion result and does not even have to be interrupted in this case. So, as soon as the ADC conversion result is ready, the PTG can take some further actions and external interrupt as well. So, what does this command look like? You basically populate this step registers with this particular value, constant value, and along with parameters that specifies which exact peripheral event you are waiting for. And then there is also an option for a software trigger. So, here in this case it is waiting for a trigger from the CPU instead of any peripheral module. So, if you enable this, if you perform this step command, software trigger enable, then it will set and wait for software trigger from the CPU. The CPU has to set a particular control bit in order to for the PTG to get that trigger and go into the next step. The output triggers are also possible, and there are in fact more output trigger destinations than there are input trigger sources. So, you could send a PWM synchronization signal, or you could send an event trigger to the input capture, or even output compare, or even a comparator mask. So, comparator mask is basically a temporary signal that you use to specify that the comparator should not change its state during that period. So, those are periods that where you do not want the comparator to be functioning. It is a very temporary signal. So, this could send a signal that does that as well. ADC sample. So, this is basically a trigger that the PTG sends to the ADC, telling it to start sampling the next signal in its that is assigned to it. So, this would initiate the sampling and conversion sequence, and then the input trigger would happen when the ADC conversion results are ready. So, these two provide some kind of a polling mechanism without involving the CPU at all. So, that is what the command looks like. You have to specify which specific hardware output you are generating. Yeah, question.
My question is, if I have, for example, many input signals to monitor, but
okay.
Probably I get stuck for the instruction of WHI.
Mm-hmm.
So, if I can't, if the first input signal just lost or just not happens, how?
Yeah, the question is if you are waiting for multiple in your application, you might need to wait for multiple input triggers at the same time, multiple peripheral events, but the step command would wait for each input trigger sequentially. So, yes, that could end up delaying the response to the next trigger, but yeah, that is probably one limitation. It is an important, interesting point, because they are all handled sequentially. So, you wait for whatever is the most critical input trigger, and then the next one, and so on. But yeah, it's not unlike for output triggers, where there is such a thing as broadcast trigger. So, you can generate triggers to multiple peripherals at the same time. but for inputs there is no like a logical or anything like that.
If
You have to, it's a bit field where you have to select certain input.
he has got his own watchdog timer, is it
Yes.
possible to reduce that
Yeah,
watchdog timer?
of course.
And will it reset the whole module, or it will allow you to continue the next step?
Watchdog timer, when it times out, it will stop execute, it will yeah, I need to check on that, whether it goes back to step 0
Oh, yeah.
or whether it continues from that step when you restart it.
That way you can overcome
Yes,
this problem.
absolutely.
Or you could possibly use the CLC. Just look at multiple inputs and go find out which event happened.
Right.
You don't have very many instruction steps, but
Yeah.
it's a possibility.
Yeah, the only problem is that the devices that are currently released do not have both CLC and PTG together. So PTG does not have a hardware input trigger from the CLC on the existing devices. Newer ones might. Yeah, as we have devices with PTG and CLC together, then there would be triggers. So the CLC can be used to combine those multiple peripheral events, then maybe a logical OR.
How many PTG? I mean, in the most how many PTG may exist on one chip?
Right now, I think it is one PTG.
Only one.
Yeah, but there could be more. I mean, on larger memory devices.
So probably, I mean, if we have multiple input signals, we can configure
Yeah.
one input signal for one PTG. That
Yeah.
will-
In fact, what an interesting architectural enhancement probably would be is to for one PTG to be able to trigger the other PTG, something like that. So PTG to be available as a trigger source or trigger destination to the other PTG. But so far, I think all our devices have only one PTG each. So it can generate triggers to multiple peripherals at the same time by setting a specific value in that PTG control register, and it can also generate up to 16 interrupt requests to the CPU. So depending on which interrupt request happened, the CPU can take different actions immediately. So it can be a very specific, event specific interrupt. And this is again independent of the peripheral interrupts that may be happening. I had mentioned about the PTG strobe command, and you can see it in action here. The ADC channel select register is typically the register where you select which analog inputs each ADC sample and hold would be sampling, right? And there could be multiple such sample and holds. So this command allows you to update these channel select registers in runtime. Runtime meaning as the PTG step commands are executing. And why is that useful? Because how else would you do it? So here you would store some alternate value for this any of these registers in the PTG hold register, which is a special holding register. So you would set that up in advance, and then as and when needed, you would execute a PTG copy command, and that value would be transferred into whichever register you specify. It could be either of the loop counters, it could be either of the delay timers, it could be the PTG literal register, which is used for the ADC channel select. And on the other hand, you could also use PTG add. So the difference between PTG copy and PTG add is PTG add adds a certain adjust value to the current contents of that register. So let's say the timer value, the timer limit register right now contains 100, and your PTG adjust value is 50. So then once you execute a PTG add command, your timer delay would change to 150 and 200 and so on every time you do it. So if you want to periodically increment or decrement your any of these register values, your loop counts or your timer limits by a certain offset, you can do that very easily using the PTG add command. And finally, there is the PTG loop control features, which are basically unconditional looping or conditional looping. And I'd already mentioned about this, that once you execute a PTG jump command and you specify which step number you want to jump to, it will immediately start executing that specified step command or step number. So you can use this to repeat a whole block of PTG instructions, PTG commands. And similarly, conditional looping, it continues executing this block until the loop counter 0 or 1, whichever you are using, decrements to 0. And then it executes and moves on to the next step command in that sequence. So how many loops can you nest inside each other? Any idea?
2.
You can nest 2 conditional loops inside each other, and you can also have an outer unconditional loop. So you can have as many as 3 loops running inside each other, because you have 2 loop counters plus you have the unconditional loop. So here is the next pop quiz. Oh no, this is the first application of the PTG, is to generate some kind of complex waveforms, right? And we'll take the example of a frequency sweep generator. But there are various complex waveforms that can be very easily generated using the PTG, and we have tried all these out in one of the application notes. There is constant or variable frequency square waves, PWM waveforms. You could generate a frequency sweep signal, and that's what we'll look at. And then you could also generate delayed one-shot pulses. So you could generate a one-shot pulse, or you could also trigger off an incoming pulse and use that and use a specific delay and generate an output pulse. So there are a lot of different things that are possible. Or you can combine it with other core independent peripherals and even generate some analog waveforms, maybe the op-amp and comparator and so on. So for frequency sweep generator, we can very efficiently use the PTG, and we'll look at that implementation. But basically, what are frequency sweep signals useful for? Maybe for testing a lot of analog circuits, instruments, calibrating different instruments and so on, even for testing communication equipment. And a real life application, maybe the PTG can be used in conjunction with output compare and DMA. To implement the frequency sweep generator. But in the application we'll look at today, which is what we have used in the app note, you basically use the PTG with a simple IO pin. So the PTG would generate an interrupt request and the CPU would toggle an IO pin. But the main role that PTG is playing here is to update the frequency of that pulse or the period of that pulse consecutively. Right. So initially it has a very low period or high frequency, and then gradually the period keeps increasing, then it reaches its maximum value, and then again it rolls over and starts from its lowest period possible. So it cycles through the whole range of periods at a certain updating the period with a given offset and each iteration. And this is an ideal case for the PTG add command, because you can use the PTG add command to increment the timer delay values, right? So if you add a specific offset to it, each time the period keeps increasing in steps, and then finally it reaches the maximum and then rolls over. But you could also use the PTG copy command if you want to generate arbitrary periods, or maybe you would want to generate so many pulses of a certain frequency and then change it after a certain number of pulses. So there are a lot of things that are possible here. So how would you do it? It only requires 4 PTG steps. That is assuming an IO pin toggling is used to generate the actual waveform. And as you can see from the hand symbol, this is one of the hands-on labs in the Open Lab session 20011. So initially you generate a CPU interrupt, so that the CPU would then use that interrupt service routine to simply toggle an IO pin. It will then return back. And then in the second step, which is step 1, what we are doing here is to initiate or start off timer 0 or any of the 2 timers, and also wait for it. So this same step command, this control command, will start the delay timer and also wait for it to time out. So it's effectively a delay step. And this timer period value would obviously vary, as we'll see. So in the next step itself, what we do here is to execute a PTG add command to increment this timer delay. So these different numbers here would specify different registers that need to be incremented. So in this case we have chosen the one of the timers, and this is the on the internal timer of the PTG. So the PTG add command would increment it based on whatever the increment amount would be whatever has been pre-set up in the PTG adjust register. There is a register called PTG adjust. And then in the next step we are basically jumping to step 0. So this is an unconditional branch. So it will keep executing this, and the main difference is that every time on every iteration the period keeps increasing, and at some point it will reach its maximum value and it will roll over, and then it starts from the lowest value again. So just in 4 PTG steps we are generating a frequency sweep square wave signal. And all that the CPU needs to do is to service the ISR by toggling an IO pin. But in a real application, if you are using output compare or something like that, you could even eliminate that as well. So you could trigger the output compare would generate the square wave, and you could even use DMA to update those duty cycles or periods if needed. The next application we will look at is something that is very practical, dynamic control of ADC channels. We have already looked at that to some extent because in some cases the ADC channel selections need to be switched in different parts of your application, okay, or between different portions of different portions of a waveform you would need to sample some different analog signals. So this allows you to do that because through the PTG strobe command. And of course this eliminates CPU processing and reinitialization overhead, because the CPU does not have to disable the ADC module or wait for any analog stabilization time and so on. The PTG is doing all this in the background. And here is a real scenario where, let's say, there is a waveform and there are multiple cycles of this waveform, and you might need to sample different signals in each cycle, okay. But within each cycle itself you should only start sampling after the signal has reached a certain value or after a certain delay, let's say. So in this case let that delay be denoted as 2, and then what it is doing is, for greater accuracy, it is taking multiple samples. So it is sampling the ADC in a burst mode repeatedly, which you normally cannot do. You would have to cycle between one input and another through scanning and all that. So here it is taking n number of samples, which could be anything, let's say 25 or 10, and then the CPU would take these samples and average it out for maximum accuracy. So it only has a small amount of time required to do that. So let's see what's happening here. So the initial part of this sequence is getting a trigger input to PTG, right? And then the PTG imposes a certain delay, and only after that it sends a trigger to the ADC to sample that particular analog signal. And it needs to do that so many times, right, because it is taking multiple samples, and between each successive sample it again needs to have some delay that would determine what that conversion rate is basically. So it's there's a delay, there's an ADC sample request, there's another delay, another ADC sample request, and so on, and you specified how many times you want to sample it. And once that's done, you need the CPU to average out that data, right, the conversion results. So you have to, so it generates a trigger and a PTG IRQ basically. So the CPU can service that interrupt, compute the average, and then it gets the next trigger. And the same cycle repeats, but in this case you have noticed that the PTG would have changed the analog channel selection. So it's now sampling a different channel. The next time it's sampling a different channel, and so on. So there are two roles it is playing here, right? One is to insert these delays and perform multiple samplings, and also to switch over the channels from one portion of the waveform to another. So how would you do that? You would do this using maybe 9 steps So initially it would wait for the whatever is the initial input trigger, that's happening in step 1, and then in step 0, and then in step 1 PTG strobe command. So this is where it's actually changing the ADC channel select register value. So it has so it's specifying in the command in and then PTG CTRL is 8, which so this is where it's not triggering, it's this is a delay, this is the initial delay after which it starts sampling the ADC channels, and then it sends a sample request, it waits for the conversion to be done, and then it branches back to step 3. So this step 3-step block, it performs as many times as the number of samples it is taking. Okay. And after that it sends an interrupt request to the CPU to compute the average, and then you see a PTG add command here. So here what it is doing is to it's continuously updating that not the ADC channel select register directly, but the holding register that will be later transferred to the ADC channel select register. So here it's updating that temporary register, and then in the next iteration it will actually transfer that channel selection value to the ADC control register, right. And of course at the end it's a unconditional jump, so it will keep repeating this entire sequence. So just using 9 steps that are running completely parallel to the CPU, it's able to execute a relatively complex sequence of events, and all that the CPU needs to do in this case is to compute an average. So next pop quiz, this is on the ADC on the PTG module. The PTG module can be used to do the following: change ADC channels on the fly, or generate a delayed one-shot pulse, generate a swept frequency signal, or all of the above. Yes, all of the above. Any questions on the PTG? Because I know this is a little tricky as a module, but once you start using it, you'll find it to be very versatile, and you can use it in a variety of ways. So it all depends on your creativity, pretty much. So let's now look at another module that's very useful, especially for eliminating external analog and digital analog circuits, and that's the on-chip programmable gain amplifier, or PGA module. So this is a much simpler module than the PTG, because all it contains is an op-amp and some internal resistors that you can control. So you don't need any external resistors at all, you don't need any external op-amp either. If you want to, if you have some small valued signals that you want to amplify, you can do that very easily using the PGA. It has a high gain bandwidth product as well. So there are some control bits that you need to set up or change to change the gain of this op-amp. So right now it's not a full range, you cannot change it to any arbitrary gains, but a certain range, a certain set of specified gain values. So this is how you set it up, and there are multiple inputs provided. You can either use it in a differential manner, or you can hold the second input to ground and use it like a single-ended amplifier, and of course you specify the gain. There is also an automatic calibration feature. So during production tests, some in the flash memory area or test memory area, there would be some values that are stored. So all the your production code needs to do is to read those values, write it to that register, and it will self-calibrate itself. That's to account for the process variations between devices. And what do you do with the PGA output, which is the amplified signal? You can either send it out through an output pin, which is basically shared with the DAC out function, or you can send it to the as a comparator input internally. So based on that input, based on that signal value, the comparator can generate a high or low, and for example that could be used as an output compare fault or PWM fault signal directly. So it doesn't require any external connections, it's internally remapped to as a comparator input. Similarly, it can also be internally used as an ADC input signal, and we will see why that is useful. And that is, for example, in this application scenario where you are performing interleaved power factor correction, right. So, here you would need to measure the phase currents and over across shunt resistors, right, and those are very small valued currents. So, typically you need to amplify it quite a bit, and then it is directly routed to the ADC input. So, without any CPU intervention or without consuming any external pin connections, you can directly use this amplified signal and use those ADC conversion results to perform your PFC control loop and so on. In fact, here you can use the PTG to wait for those ADC conversion results and then trigger send an interrupt request to the CPU, and the CPU can then execute the control loop. So, you can even use this in conjunction with PTG or other modules. So, next pop quiz, which of the following features is supported by the PGA module? Rail to rail operation from 0 to 3.3 volts or 0 to 5 volts depending on the device. Gain can be selected without using external resistors. Users can choose between single ended or differential mode, or all of the above. Yep, it's all of the above. So, finally, we look at the analog comparators and operational amplifiers, and this section again you may have seen if you have attended CIP2 class. So, all our 16-bit devices have multiple comparator modules, maybe 3, 4 or more, and each of these has its own different input selections. So, you can choose between multiple inputs, and also you can choose multiple reference voltages. It also has an on-chip reference voltage that can be generated or configured. So, it can be used again in differential manner, or in can ground one and feed the signal onto the other. And note this, the two output blocks called blanking function and digital filter. We will look at that in the next slide, but these are enhanced features present especially on the dsPIC devices or even the most recent PIC24F devices. But some of these comparator modules can alternatively be configured as an op-amp as well, and we will look at that in a little more detail, but basically the same module gets reconfigured as an op-amp, and in that case the output is of course an analog signal, amplified analog signal, which you can feed to an output pin, or you can feed in directly as an ADC input, just like you did for the PGA. And a very useful feature here is that it can directly generate PWM faults internally. So, there is virtual pin remapping which allows the comparator outputs to be directly provided as fault inputs to the PWM module. So, you do not need to provide any external circuitry to scan for currents or generate those faults, and you do not even need to do any external rerouting of the signals of the pins. It is all connected internally, and you get the PWM shuts down as soon as it receives that fault. So, what are these blanking and digital filter features? So, blanking is where there are certain periods when you do not want the comparator to change state, and this is typically to periods where you would expect a lot of switching transients. So, a lot of MOSFET switching in your circuit, and the waveform might actually fluctuate a little bit very close to that voltage threshold, right, the reference voltage. So, the comparator will then go back and forth and cause some kind of ringing which can damage some external circuits. So, during those transition points you can provide a blanking signal which is basically a temporary pulse that will prevent the comparator from changing its state. And similarly, the output signal can also be passed through an internal digital filter, and that is to avoid the effect of electromagnetic interference, because if there is sudden EMI signals imposed on the comparator circuit, it could cause some glitches, which especially in automotive or industrial kind of environments. So, the digital filter would suppress those kind of glitches.
Where
Yeah.
does the blanking signal come from?
Yes. The blanking signal can come from a variety of sources, and it can even be I think there are some logic functions as well. So, you can combine different signals in logic OR and logic and use that to generate the blanking signal. It comes from other comparators, it comes from timers, compare, output compare and so on. So, here is another application that kind of combines comparators along with the CLC module which you saw earlier. So, you may have seen this application if you attended CIP1 class as well, but we will go over that here too. So, here we are trying to detect the phase difference between two input signals, okay, which is useful in many applications, whether it is power supplies or distance measurement and so on, power factor correction. And for this we need two comparators if the input signals are analog signals. So, let us say they are sinusoidal waves, you need comparators to serve as a zero cross detector. So, you basically convert that into a square wave. But if the input signals are digital signals or square wave signals, then you would not need these two comparators. You can directly provide the signals into the CLC modules. And you would need two CLC modules. The first CLC module is only used to generate a pulse that would be proportional to the phase difference between those two signals. So, if it is completely out in phase or if you provide the same signal to both inputs, it would be completely low signal. If they are 180° out of phase, then it would be a high signal at the CLC1 output, or if it is some other phase in between, let us say a 90° phase shift, it would be a almost a 50% duty cycle. And then CLC2 module is used to determine if this first signal is leading the second signal in phase or the first signal is lagging the second signal, and that is how it would look like. So, for CLC1 you would provide basically the two signals in an XOR fashion. So, does CLC have an XOR mode? If you remember, do you remember? It does not natively have an XOR mode, it has an AND OR mode and I think some other mode as well. So, here we are using the AND OR mode to generate an XOR function. That is simple, A or and B bar and or A bar and B. So, you just need to complement one and feed it into an AND gate, and then the reverse polarity is on the other one and then OR it. So, that will end up generating an XOR gate. So, here if they are completely in phase, obviously the XOR output would be completely low, but if they have some phase difference, it would generate a pulse that would be proportional to that phase difference. So, in a real application you might need input capture to actually calculate and quantify that phase difference in terms of degrees. But I think in the hands-on lab, in the open lab session, we are just observing the outputs on an oscilloscope, and in fact we are just feeding 90° phase shifted signals. So, it is not a variable output really. And then the second CLC module is used in a D flip-flop configuration. So, you feed one signal as the D input, the other one as the clock, and you get the lead lag information. Another possible application is for multi-parameter monitoring. So, applications like let us say if you are controlling an industrial plant or controlling some kind of machinery, you might need to monitor different parameters, right, temperature, pressure, humidity, fluid level, flow rate and so on. So, how would you measure and monitor multiple parameters to make sure that they are staying within their permissible limits? So, if let us say the temperature gets too high, you would want to shut down the plant, for example, or if the flow rate also becomes too high, you might want to shut down some valve, right. So, using comparators and CLCs, you can combine many of those parameter measurements together and directly get a high-low signal or out of limit signal, and combine those as well using the CLC, because the CLC has an OR mode and OR mode, right, and then use the CLC output directly as a control signal to shut down a plant or shut down a valve or anything. So you would basically require 2 comparators for each analog signal if you are checking for upper and lower limits of the signal value, and you would need 1 CLC per control signal, not for the input quantity. So something like this. So let us say if this represents temperature, you would have an upper bound to the temperature and a lower bound, and those would be used in the 2 comparators. So depending on whether it is crossing the upper limit or the lower limit, any one of these comparators would turn on, and if you configure it in an AND OR manner, you would get and then there could be multiple such parameters that you are combining in OR gate. So finally you will get one control signal that you can directly use to shut down some piece of machinery. So there are various things that are possible, and just using the basic functionality of the CLC, there's AND gate, OR gate and so on, not even any sequential logic. And finally we talked about operational amplifiers, but so like we saw, some comparator modules can be alternatively configured as an op-amp, and this is very useful because you would want to amplify some signals or implement some, let us say, some analog filters and so on, or level shifter. There could be a lot of discrete or external circuits that you would need that you can now bring on chip by combining some of these op-amp modules together. So any kind of signal conditioning, you would reduce the need to use external op-amps. You would still need to use the external, resistor, capacitor kind of elements, because you would need to control the gain and so on, but it still ends up reducing the system cost and space, because at least your op-amps are on chip now. So here is an example in practical life where you can use the on chip op-amps to, let us say, generate a low cost audio signal, right. So instead of using an external audio codec or external DAC chip, you can just generate some PWM waveform using output compare or high speed PWM. So in this case, the PWM period would be basically correlated with the sample rate of that audio signal. So if, let us say, you are sampling an audio signal at 8 kilohertz, the PWM period would need to be set up to be 8 kilohertz or some multiple thereof, like 16 or 32. And then the duty cycle during each period would be updated based on the analog signal value for that particular period. So based on the sample value for that period, it would update the duty cycle. Duty cycle is in this case proportional to the analog signal level. So what you need to do is to have typically have some external analog circuitry, basically a low pass filter using op-amps to basically reconstruct the original audio signal, and that it would do by essentially averaging the signal out over each PWM period, so that so if the duty cycle is higher, the signal level would be higher during that period, the op-amp output would be higher. If the duty cycle is low, then the signal level will be low. So when you pass it through an external low pass filter, you would get the original demodulated audio signal, which is an analog signal. Now as you can see, it uses 2 op-amps which can be easily brought on chip because we have multiple op-amp modules on these devices. So all you need to do then is to connect these external discrete components. Finally, the pop quiz on comparators and op-amps. Which of the following is not possible using a shared comparator or op-amp module? Amplifying very low voltages and internally feeding into ADC without requiring an external pin connection. Generating PWM faults without needing any external circuits. So not only would you not need any external comparators or signal voltage detection circuits, but you would also not need any external physical pin connections. So internally you can take read the voltages using PWM faults, using comparators, and then directly route it to the PWM fault input. Subtracting 2 fixed point numbers or detecting abnormal signal fluctuations, basically signal limit checking. Yes, the answer is the third one. Subtracting 2 fixed point numbers is not possible using either comparator and op-amp. Why is it not possible? because both of these are operating in an analog domain and fixed point numbers are basically digital values. So you would need a CPU to perform that subtraction. So what we covered today is the whole suite of core independent peripherals that are present on 8-bit and 16-bit devices that would be relevant to mixed signal application requirements. Okay, so anything that eliminates your external analog and digital circuits or implements some interesting analog and digital signal chains in a creative way using a combination of core independent peripherals is possible using these modules. And we have also learned the features and benefits that each of these modules provides, and we also saw some application examples where multiple CIPs can combine together and work in a collaborative manner to efficiently implement some functionality or some circuits that you might normally have implemented an external circuitry for, or you would have had to implement it in software. So both things are kind of reduced or eliminated by using CIPs in working together. Here are some additional resources. It's of course many of you have attended at least one of these other 3 classes, but there is also an open lab session that I would encourage you to go for. So every day it's at 3:30 in Grand Canyon 2. So that has some 8 hands-on labs from these 4 CIP classes, 2 from each class. 4 of those are 8-bit labs, 4 of those are 16-bit labs, and 8-bit labs specifically would be using MCC as well. So if you want to, whether you want to, you're in the mood for writing some code or playing with MCC, you can still come for these open lab sessions there, because there are multiple labs that you can choose from. There are some additional application notes, and this AN2152 is one that we released very recently. It highlights various applications of the PTG module and some reference manual sections as well. And finally, there are some development tools that are all available, and most of these will be using in the hands-on labs, but also some other ones like the MPLab starter kit for digital power. So that also uses some of these core independent peripherals. And this you don't care about. So any questions on any of these modules?
I have one.
Yeah.
At times you've referenced a zero detect circuit.
Mm-hmm.
Is that a module or is that using a comparator?
Okay, so zero cross detect, is that a module or are we using the comparator? So on the 8-bit devices, it is a separate module, and it's one of the core independent peripherals. On the 16-bit devices, we have to use a comparator. So it depends on the device. Any other questions?
What is the working principle of that zero cross detect module? How
The module itself, Sean, any idea? The zero cross detect module and 8-bit. Is it just like a comparator, or it's basically a comparator with one input grounded.
Series has DCDs.
So one input is grounded all the time, or?
Well, you can choose.
Oh, you can choose. Okay, ground or any signal level. So it's basically a comparator itself. Some other name.
Comparing what? 2 signals.
Yeah, that's it. So one input you can ground the reference input, so then it will be a zero cross detect.
So if it is above 0 or and below 0, something like that?
Yeah, once it reaches 0 in that case, or you can set it to the midpoint also.
You can set it to.
Yeah.
And the output is just a square wave.
Yeah. So if you have a level shifted signal, let's say, you can set it to the midpoint, then the midpoint would represent 0, right? Signed and unsigned values. Yeah.
Because I was confusing our analog.
Right.
That
Yeah.
0 cross is not
So the midpoint is really 0 if you're talking about signed values. Right? Or if you're talking about unipolar values, then 0 is 0. So as soon as it reaches 0, it will trigger that.
Or I can set it any value.
Any value,
and
yeah.
compare it with
Yeah, it's configurable, right? There's the reference level. Okay, thank you, and before leaving, please fill up these feedback sheets because that helps us to continuously refine the classes.